I want to thank all of you to taking some time out on a weekend to join us to learn a little bit more about the exciting world of gems and the science behind it. This is a program, Gemquest, that has been going now since November 2020, and we've been on almost every month, and we've collected a lot of very interesting and exciting programs about the vast area of gemology and science associated with mineralogy as well. So I want to thank you for joining us. Today, we're going to be very, very lucky for the second time to get one of the world's leading experts, if not the leading expert, on sources of color in minerals. Now, we were privileged to have Dr. Rossman speak to us last September, and I had one of our members, I sent out a little word asking people to suggest programs, and someone said, well, how about chromium and its relationship to color in gems? And I thought, wow, the only person I know that could talk about that might be Dr. George Rossman. So on bended knee, I phoned him up and asked him, could you please give us a program on chromium? And he so very kindly agreed. And so we're going to be able to learn a lot more today than we already know, I'm sure. Just to give you a little tiny bit of background about Dr. Rossman, when he was a little tyke and started out collecting agates in Wisconsin and became interested in mineral colors at a very early age. When he took a small crystal of tourmaline to school and asked his teacher to explain how his rock could both be transparent and have different colors. His teacher did not have a clue of how to answer the question, and that set him off on a lifelong career investigating the origin of color in mineral and gems. He's now professor of mineralogy in the Division of Geology and Planetary Sciences, California Institute of Technology, Pasadena, California. He received his Bachelor of Science degree in Chemistry and Mathematics from Wisconsin State University, Eau Claire, and his doctorate from Caltech in Chemistry. His principal research interests deal with the use of spectroscopic probes to study minerals. His work addresses problems relating to the origin of color phenomena in minerals and spectroscopic methods for phase identification, just to sort of impress you with the words. He and his students developed analytical methods for the analysis of hydrous compounds in solids and their role in modifying physical and chemical properties. He's also interested in the long-term effects of minerals from exposure to background levels of natural radiation, a process important for several gem minerals. He was the recipient of the inaugural Dana Medal of the Mineralogical Society of America in 2001. So we're going back a little ways. The Richard P. Feynman Prize for Excellence in Teaching, which means I would have loved to have been one of his students, teaching at the California Institute of Technology in 2004, the Friedrich Beck Medal of the Austrian Mineralogical Society in 2005, and more recently, the Roebling Medal of the Mineralogical Society of America. Wow. It's too bad he doesn't have much in the way of credentials. He served on the board of governors for GIA and much longer on their research and advisory board. He has served as an associate editor of the American Mineralogist and is currently on the editorial review boards of both Gems and Gemology and the Journal of Gemology. He has been honored, as I mentioned in the invitations, by having 3 new minerals of the tourmaline family, Rossmanite, alumino-oxo-rosmanite, and fluorosmanite, named after him. To date, he has amazing more than 400 publications in the mineralogical and chemical sciences. I really hope that you will all enjoy today because we have one of the best teachers in the world talking to us about chromium. Mr. Dr. Rossman, please share it with us.
Thank you kindly for that introduction. Indeed, minerals are fascinating. The story of their color is equally fascinating. And today I'd like to tell you a little bit about one of my favorite chromophores, namely chromium. So the question now is, what can we know and what can we learn about chromium in a variety of minerals, gems, and other minerals as well? So if we take a look at chromium, it's a metal that used to be on the bumpers of automobiles. It's a very bright, shiny metal, but when it's oxidized into the various oxidation states, it can cause color. We think that there's chromium +2 in the lunar samples that have formed in a greatly reducing environment, but not something important terrestrially. But chromium in the +3 oxidation state is very important in a whole variety of minerals, as we will see in both the gemological and mineralogical communities. We can get chromium +5 rarely in a few compounds. We'll look at one example. And then in ore deposits where you have oxidation taking place in the upper levels of the sulfide deposits, we can often get chromium in the +6 oxidation state, which again can be extremely colorful in the mineral community. Now, we all, I think, know about chromium +3. Chromium 3, of course, is the cause of color in ruby and sapphire, the beautiful red hues that we have in a whole variety of things. But if we look at another oxidation state of chromium, here's chromium +5. This is the phosphate mineral pyromorphite, where chromium +5 actually replaces a small amount of the phosphorus, and it gives this beautiful green color, something not particularly common, but an example of a beautiful color caused by chromium in a much less common oxidation state. And then, of course, we have chromate, chromium in the +6 oxidation state. And in a whole variety of ore deposits where we have chromium, where there's oxidation taking place, rainwater percolating into the upper levels of the ore, carrying dissolved oxygen, the chromium can over geologic time become oxidized, and you get the chromate, like crocoite from Tasmania, the beautiful orange color. You see it in wolfenite and a variety of other minerals, where small amounts of chromium in the +6 oxidation state enters and gives typically beautiful orange colors to a lot of these interesting minerals. But today our quest is going to be more focused on the gem minerals. So where better to start than perhaps with ruby? Now, I think that all of us probably know that chromium is the cause of color in ruby, but the thing that we want to look at is historically, how did we learn that this was the case? We have beautiful gems, beautiful crystals. In the lapidary world, beautiful carvings like the one you see here are made out of ruby. And in all of these cases, the cause of color is chromium. But we might want to ask, how do we know what causes the color? How do we study color? If we have an unknown mineral, how would we understand what the color is? And historically speaking, going back more than 100 years, how did we understand that chromium is the cause of color in the ruby? Well, what we have to do, at least in the analytical labs that I work in, we have to chemically analyze the mineral. We have to see which elements are inside the mineral. And we often can find there's a variety of potential candidates that might be causing color. So the absolute best way to really understand what's going on is to synthesize the mineral. And we take very pure chemicals, like aluminum oxide in the case of ruby, and then add small amounts of what we think may be the chromophore. And after we synthesize it, we see if we get the color of the gem. And then we also, of course, want to study the spectrum, look at the way it absorbs light. Very often, this gives us a very good clue of where the cause of color is coming from. But it's a little difficult sometimes to make a firm decision on the cause of color just from the spectrum alone. So the synthetic method really is the key way of absolutely proving where color is coming from. Now, how would I go about the problem of analyzing where color in these minerals comes from? Well, the first thing I would probably do is put it on a machine that we call X-ray fluorescence. This is a machine that takes a small crystal of the material, or even some powder, and we can shoot high-energy X-rays at the sample. We knock electrons out of the atom, and then the electrons inside the atom rearrange and give off very characteristic wavelengths of X-rays as they move in their energy levels. And all these different X-rays that come out in the process are diagnostic of the different elements: chromium, aluminum, manganese, iron, strontium. All the different elements have their characteristic X-rays. So it's a very fast, a very simple way of getting a chemical analysis. It gets you down to the 10 part per million level pretty rapidly. It's not extremely expensive. It's not the most accurate way in the world to do it, because oftentimes we have to do it with standardless analysis because we don't know what the chemistry is necessarily to begin with. But we can get totals that are like 90% accurate, and we can get a very good idea what's inside the mineral. If we want to be a little bit more accurate, we use scanning electron microscopes. In these instruments, we have a beam of electrons coming down in a vacuum, 15,000-volt electrons that slam into the sample, and they knock electrons out of the crystals, and then other electrons inside the crystal rearrange, and they give off the same characteristic X-rays. But now we have detectors on this machine that are very well tuned to analyzing much more accurately what's going on. We have these things here, which are electron detectors. And these electron detectors can give us chemical analyses, maybe with like 98% accuracy. And typically we can get down to the 100 ppm level, sometimes a little bit lower, not as sensitive as X-ray fluorescence, but more accurate. And we can use much smaller quantities of material for the analysis. If we really want the absolute optimum in chemical accuracy, we would use the electron microprobe. And again, this is an instrument that shoots electrons down a vacuum column, hits the sample, and knocks electrons out of the sample, and then the electrons rearrange inside to fill the vacancies that were generated. But now we have a series of crystal detectors that are extremely accurate for measuring the amount of the different chemical element X-rays that are coming out. And with a machine like this, we can get accuracy of like 99.9% accurate, and we can do basically almost the entire periodic table. We can't quite do hydrogen. Lithium is kind of flaky, but from beryllium and on up, we can do a chemical analysis and analyze anything that can be put into a vacuum compartment, namely minerals and gems. Another technique that's coming to be quite popular nowadays is something called laser ablation inductively coupled plasma mass spectrometry. And in this technique, we take a high-powered laser and we shoot the laser at a sample, making a little teeny pit in the sample where we literally vaporize part of the sample, just a little, maybe 10 micrometer, 20 micrometer diameter pit. And then the vapor is swept into another machine where it's ionized and then put into a mass spectrometer. And again, you can very accurately count the number of different atoms that are coming out. It takes a little more difficulty to calibrate this machine. It's very, very sensitive for extremely low concentrations, much more than anything else. You can get down in the part per million concentrations with this technique. Not quite as accurately as an electron microprobe, but if you want to get at really low concentrations, that's a new technique that's becoming very popular nowadays, both in the analytical labs of the academic institutions like mine, and also becoming popular in some of the gemological labs. So today, these 4 instruments that I've shown you represent how we really go about now determining the origin of color, and in fact, the identification of different gem minerals. Let's take a look at an analysis. I literally yesterday went into the lab and I took 3 rubies, one from Myanmar, one from Kenya, and one from Liberia, and I put them in my X-ray fluorescence machine, and I got a chemical analysis. And as you can see, we have aluminum as we expect, and of course we have the oxide in the corundum. And yeah, we found chromium in all of these, but we found a whole bunch of other elements: silicon, phosphorus, sulfur, chlorine, titanium, traces of copper, zinc, and gallium, and rubidium, and zirconium, and tin, and uranium. Yeah, these minerals have inclusions inside them. You have little microscopic inclusions of other minerals, very common in almost all gem minerals, and those are picked up in these analyses. But if we look at the chemical analysis, we only see a small number of ones in bold that are in the concentrations where we would expect it would be important to cause color. Now, we know that silicon doesn't cause color. We rule that out. Sulfur typically does not cause color except in the case of radiation-damaged materials. We can rule that out. Titanium, chromium, and iron are the elements that way back when we would think might be important in the cause of color in ruby. Now, of course, we know the answer is chromium. We know that today. But how did that get proven in earlier times? Well, you synthesize it. You take very pure chemicals. We know there's a massive amount of aluminum and then oxygen. So we take chemically pure aluminum oxide, and we melt it up, perhaps with chromium. And this, of course, has been done. And when you do that, you find that when you grow a synthetic crystal with chromium, you get the beautiful red color of the ruby. And if you put the iron in, you don't get the red. If you put the titanium in, you don't get the red. It was easy to prove, even back in the late 1800s, that chromium was the cause of color in these rubies. Ruby has been extensively studied. It's the first solid state synthetic mineral that has been used to make lasers. So it's been extensively studied in the material science and laser community. These are some synthetic rubies. These are Judy Osmer's from a gem production. Here are rods of flame fusion ruby and a ruby crystal, and for a laser. And then here's a large boule being pulled out at the Union Carbide facility. Again, these large boules can be made either for laser technology or for synthetic gemstones. So nowadays, we know very accurately what's going on, giving the cause of color in the ruby. So let's take a little bit more look at ruby and some of the red gems. Here I am. I had great fun holding one of the largest rubies that exists, more than 10,000 carats, in a crystal from Myanmar. And of course, we know that chromium in ruby causes the color, but ruby is not the only mineral where chromium causes color of this beautiful red variety. We also have spinels. When I went to Myanmar, I picked up a lot of these. They were readily available. Beautiful red spinel, gem quality material. And again, in these spinels, chromium in the +3 oxidation state is the cause of color. We can easily analyze these materials and find out that chromium is the dominant chromophore. So let's take a spinel and let's take a ruby and let's make, in my world, a window out of it. We make a slice and we make basically a flat plate of known thickness, and we shoot light through it and we measure in a spectrometer what wavelengths of light are transmitted and which ones are absorbed. And here's what we see. Here we're comparing the trace of the ruby, the red trace, with the trace of the spinel, the one in black. And what we see is that both of these minerals are absorbing, as the curve goes up, very heavily in the purples and in the blues. And then we're absorbing in the greens, and we're absorbing into the yellows and slightly into the orange. But dominantly, in each of these minerals, we are transmitting red light. So some of you might use a Chelsea filter, and these are the filters that when you put on minerals, and if you see red light coming through, you suspect indeed it might be chromium causing the color. And as you can see in these two minerals, the major region where light is transmitted is in the red, and that's why the filter works. But it's not absolutely certain that it's chromium. For example, vanadium and a few other elements will also transmit light in this region, but it's a good hint. But on the other hand, with the chemical analysis that we do in the spectrometry, we can tell for sure that it's ruby or spinel caused in color by chromium. Now, there is some bluish light coming through in each of these. That's why we don't have a pure red color. We have more of a slightly purpley red color, and it's a little bit of greenish blue or bluish purple component coming through that modifies the color. And in my world of high quality spectrometers, this little sharp feature we see here near 700 nanometers is another feature that we often see in chromium. And again, that's a pretty good giveaway that we might be looking at chromium. Now, the reason the Chelsea filter works is that a lot of other things that contain iron, a very common element, absorb pretty strongly in this region, where chromium doesn't have absorption in this region, and that's why the simple filter technique gives you a relatively good indication that it might be chromium. Okay, but it gets a little bit more complicated in terms of the absolute science going on here. We have other phenomena in the minerals that contain chromium. We have dichroism and we have pleochroism. Now, I think you all kind of know about these multiple colors, but this is a situation where when you look at the crystal, either in different orientations, holding and rotating the crystal, or more effectively, if you use polarized light and look at the light in different polarizations coming through the crystal, you see different colors. It's called dichroic if you see two different colors. and tetragonal and hexagonal crystals do that. And it's called pleochroism if you see three colors, and the orthorhombic, monoclinic, and triclinic crystals do that. So before we get into a detailed study of the gems, let's take a look and ask a question. What does chromium look like in ruby in these two different polarizations? And here's a large synthetic boule of chromium on the left. If you make a little window out of it, you can see when you shine in polarized light that's parallel or perpendicular to the z-axis, you do see somewhat different intensities of color, kind of a pink and more of a purpley red color. This is very common in a lot of minerals. And the question is, why does it happen? So let's take just a brief interlude now into the science behind this before we look at the individual gems and understand why we get this phenomena of dichroism in ruby. Well, it has to do with electrons. All these gems are containing atoms, and the atoms have electrons. And as I hope you know, the electrons occur in orbitals, and the orbitals have certain shapes and volumes where the electrons travel. And if we had a 6-coordinated environment, 6 oxygens around the chromium, which is what you have in ruby, you would expect to see 2 of the orbitals at somewhat higher energy and 3 of the orbitals at somewhat lower energy. And if we look at the chromium, we find that the lower 3 orbitals each have an electron inside them. Now, if we shoot light, that is energy, at a ruby, we're going to take one of the electrons that's downstairs and move it into one of the upstairs orbitals. That's the process that absorbs light in these minerals. But before we do that, we have to take a little look again at chromium in the aluminum site where the chromium occupies in the ruby. Chromium replaces aluminum in the ruby. If you look at the aluminum in great detail, which people do with X-ray techniques, you find that the aluminum oxygen distance in corundum comes in 2 different distances, one slightly further away, one oxygen further away from the chromium, and one oxygen closer to the chromium. And we also find that the bond angles, that is the angle between the oxygen, the chromium here, these angles right in here, they're not 90 degrees, they vary from about 80 to 101 degrees. And this has a lot of consequences for the property. When we're going to shine light at the ruby, we might move an electron from the chromium, which is down here in the center, up to one of the electrons, towards one of the oxygens that's further away, or we might move it to one of the oxygens that's closer, and that has important consequences. If we move that electron from downstairs in energy to a higher energy orbital, we might move it to an oxygen that's further away, and there's going to be less electrostatic repulsion. The electron in the orbital is further away from the neighboring oxygen ion. Oxygen has 2 negative charges on it, and the negative charges on the oxygen are going to repel the electrons in that orbital. So it's going to take more energy to put the electrons in that orbital because of the repulsion that it has to overcome if the electrons are close to the oxygen. But if the oxygen is further away, there's going to be less repulsion, and it's going to take less energy to make that electron go upstairs. Less energy makes a lower amount of energy in the light that moves the light closer to the red. If it's more energy we have to take to make that electron move upstairs because of the repulsion, we move the absorption closer to the blue. And there's another complication. If the bonds are bent, so if the orbitals are vertical, but the oxygen is bent off to the side, like over here, when the electron goes upstairs, if it collides directly with the oxygen, that's going to be more repulsive. It's going to take more energy to make the electron go up there. But if the oxygen surrounding the chromium is a little bit bent off to the side, the electron is going to be repelled, but it's not going to be repelled as strongly if it's not colliding directly with the oxygen. And that's going to be a lower energy amount of light that's necessary to make that electron move. And all this means that if we take a look at chromium, we're going to see that if the light goes perpendicular to the z-axis, we get slightly different absorption. Notice the wavelengths of these absorptions in the different directions are slightly different, reflecting different amounts of energy. If we go further to the left, it takes more energy. And the intensity is different. The probability of that electron moving is different because of these repulsive effects. So the intensity of absorption will be different in the two different polarizations. It's kind of complicated in intimate detail, but the basic principles are that the electrons are repelled by the oxygen atoms surrounding the chromium, and that's going to change the amount of energy and the probability that those electrons are going to move, and that's going to be the cause of the dichroism in the ruby and why we get these two different colors. Well, chromium has another color in minerals, green. Oh my gosh, look at that. You all know that emerald is green. You have some of the amphiboles like actinolite that are green. You have the hiddenite variety of spodumene that is green. You have the garnets that are green like uvarovite and grosschiter. And you get chrome tourmaline that is green. And you get, my gosh, jadeite, one of the most important gems in Asia. And you get chrome diopside that's green. There are a whole variety of minerals, many, many other minerals that are green because they contain chromium. Let's take a look at emerald, for example. Here's an emerald crystal, and these are a couple of different emerald gems. They're a beautiful green color. If we take a look at their pleochroism or their dichroism, it's much paler than it was in the case of ruby. We don't see as much of a difference in the colors, whether it's unpolarized or polarized with parallel or perpendicular to the z-axis. Let's take a look at the absorption spectrum. And now we see that the differences in the intensity of the absorptions in the different directions aren't as severe as they were in the case of the ruby. The energy it takes to move those electrons is rather comparable, irrespective of whether they're going parallel or perpendicular to the z-axis. So we get less dichroism in the case of the emerald. And again, we see that little sharp feature, not a pretty sharp feature actually near 700. This is a diagnostic feature of chromium. So again, we know this is chromium causing the absorption. Again, we see there's more light coming through out here, but look, this is so far into the red that the human eye is not very effective in seeing these deep, deep red wavelengths. Now the maximum transmission is in this region here where the green dominates, and the human eye is spectacularly sensitive in the green. So rather than seeing the red, which is just barely coming through in wavelengths we can't really work with very well, we see the green color, and that's why the emeralds and all these other minerals are green. We have shifted the wavelengths that these absorptions take place because of the difference in the oxygen distance from the chromium in these minerals. Wow. But that does raise a question that we need to explore a little bit more in detail. Why aren't rubies green? Why are they red? Let's take a look at that in more detail. We have beautiful green beryl, we have beautiful green garnets, and we have red rubies. So why are rubies red, not green? Well, as I kind of hinted before, it has to do with the distance of the oxygen atoms away from the chromium. If we take a look at beryl and garnet, the oxygen atoms are further away from the chromium than they are in the case of the ruby. In both in the ruby and the spinel, the oxygen atom is only about 1.91 angstroms away from the chromium, but in the beryl and the garnet, it's a greater distance away. Because it's further away, it takes less energy to move that electron into the upstairs orbital. It's going to shift a little bit to lower energy, and it's this distance, the chromium-oxygen distance, that's the cause of the difference of the color in these minerals. And the distance is 1.98 or 1.91 is set by the structure of the mineral. Whatever host the chromium enter is going to be basically dominated by the properties of the host mineral. It doesn't change everything to suit itself. It's going to be forced to comply with the structure of the mineral. So where the oxygens are further apart, you get the green minerals. Where the oxygens are closer to the chromium, you get the red minerals. And we can see that in the spectrum. If we take a look at the spectrum, which we can see in any type of spectrometer, we see that the transmission regions where those crystals are not absorbing is different. Over here in the red, it's lower energy. Over here on the left, it's high energy. The absorption of light in ruby takes place at higher energy than it does in the green garnet. And again, the second absorption band in the ruby takes place at higher energy than it does in the green garnet. And more importantly, the window where light is transmitted moves to lower energy where you have longer chromium oxygen distances, letting the green light come through, where when it's shorter, you get the red light coming through. But in the green minerals, the red region is pretty much absorbed by the absorption band of the chromium, so you're dominated by the green, where in the rubies, we're dominated by the red. Very simply in concept, that is simply the size of the site the chromium goes in determining the color. Now, we can do an interesting little experiment. We can take a ruby and we can heat it up. When you heat something, things expand. So if we take a ruby and heat it, oh my gosh, you can see that these absorption bands, as you increase the temperature, move over to the right. That's to lower energy. As the crystal expands, the oxygen atoms get further apart and the bands shift. And I wonder if that would change the color. Well, let's try that. Let's take a ruby, make a little slice out of it, and put it in a furnace and heat it up and see what happens. Here we go. High temperature is orange. Coming down at low temperature, it's red. Going back up to high temperature, it turns orange. Coming back to low temperature, it turns red. Heating a ruby changes its color. Pretty interesting little experiment. But we can, a little bit later, get a more exciting example of this. But let's first take a look at some green chromium minerals. These are garnets, uvarovite garnet, which in most cases is a mixture of both chromium and aluminum inside the garnet. It isn't really pure chromium in almost any real case. It's a mixture of both minerals, or both elements rather. But it's the chromium that causes the green color in these uvarovite garnets from different places around the world. And same thing in grossular. There are many localities around the world where you have a little bit of chromium replacing the aluminum in the grossular garnet. You make these beautiful green garnets from Canada and other places due to the fact that we have a little bit of chromium replacing the aluminum. Now here's savorite garnet. I think all of you know that savorite garnet is caused by vanadium. Vanadium makes it green just like chromium. This is a gemstone I got from Bruce Bridges, which I analyzed, and vanadium clearly dominates over chromium. But here's the sample from the Scorpion mine I got from Campbell Bridges. And oh my gosh, chromium in this particular garnet dominates over vanadium. Some of the savorites, in fact, many of them are vanadium dominant, giving them green, but some of them are chromium dominant in the chemistry, but they're also green, and they're basically impossible to tell apart by naked eye. You have to go to a chemical analysis to see whether you have a chromium or a vanadium grossular in the savorite family of minerals. Now, what about demantoid, the chromium-containing variety of andradite? In demantoid, chromium replaces a little bit of the iron in the andradite garnet. But chromium is an extremely strong chromophore compared to iron in most cases. And it just takes a few tenths of a weight percent of chromium to totally overpower the color of the iron itself. So put in a few tenths of a weight percent chromium in a demantoid, and you see the green color of the chromium, not the very, very pale color, the yellowish green of the iron itself. Now, you also can get chromium in pyrope. Pyrope has a somewhat different structure from andradite in terms of the metal-oxygen bond distances. And when you get chromium in pyrope, you get the reddish color. This is a kimberlite dike from Moses Rock, Utah. You can also get these from some of the kimberlites in Africa. When you have chromium replacing some of the aluminum in these magnesium garnets, just a few tenths of a weight percent, the spectrum is the chromium spectrum. The red light, like we saw in the ruby and the spinel, is coming through, a little bit of blue light coming through, giving the purpley tint. This is what they look like. Not extremely common in the gem market, but nevertheless, you can get chrome pyrope as the color. Now, what I wanted to do is to see what would happen if I could heat the crystal of chrome pyrope and expand it to make the metal oxygen distance increase. Could I change the color of the pyrope by heating it? So let's go ahead and do that experiment. Green at high temperature, red at low temperature. Coming back up, green at high temperature, red at low temperature. When you heat a pyrope, you can expand it and you can change from the red color of the ruby to the green color of the garnet simply by expanding the metal oxygen distance in these crystals. You're not going to heat your gemstone, I'm sure, but it's a kind of a fun experiment to prove the principles. Now let's go to chrysoberyl. This isn't green, this isn't red, it's blue. And again, the metal oxygen distances for the chromium that is replacing some of the aluminum in the chrysoberyl are such that you don't get the pure green, you don't get the pure red, you get more of a blue color instead. Yeah, life can get complicated. Not all minerals have the same metal oxygen bond distance. And if we look at that, we can see the spectrum. We can see that the light has now moved down to the lower energy region where it's absorbing a lot of the reds. We don't see the reds anymore because they're absorbed by the strong absorption of the chrysoberyl. We see the little sharp feature that's dominant of the chromium, but now the window has opened up in the blue region, slightly greenish blue. This is where we see the color of the chrysoberyl. There's very strong dichroism, as you can see on the right-hand side. The intensity of absorption in the two different polarizations is very different, but nevertheless, it's neither red nor green. Here we have an example of a different color caused by chromium. Another example is topaz. When I was in near Ouro Preto, a little bit to the southwest of Ouro Preto, in the big imperial topaz mine, some of the samples were coming out with kind of a brownish red color. The brown color in these topazes come from radiation damage. When the topaz sits in the ground, it absorbs the gamma rays from radioactive potassium. Potassium is common in feldspars and clays and other minerals. Potassium has a small amount of a naturally radioactive isotope, potassium-40. It's a very, very long half-life. But over geologic time, these crystals slowly get irradiated, and you get the brown color developing. But if there's chromium in the topaz, that happens occasionally, you get the brownish red color, and then when you heat them, the brown goes away as you destroy the radiation damage, and you're left with the pure pink, or if there's a lot of chromium, a pure red color in the case of these topazes. A very, very beautiful gem, but not particularly common, but nevertheless, it's one of the components of the imperial topaz that we find in the formerly active mines in Brazil. Zoisite. Here's a ruby in zoisite. The ruby is the red, but the green color in the background is zoisite from Tanzania. And the zoisite in this case has some chromium replacing the aluminum. And again, we get the green color, a beautiful example of green and red. Typically, this is more of a lapidary product. I don't think I've ever personally seen a high gem quality green zoisite. The gem zoisites tend to be vanadium colored, blue. But in principle, one could get a green one if you have chromium rather than vanadium replacing the aluminum. And here's some other minerals, perhaps a little bit less common. Titanite, sometimes called sphene in the gem market. You get these beautiful green colors like we have over here from the Tanzanian material, where a little bit of the titanium is going to be replaced by chromium. Then other chemical substitutions take place for charge balance. Not particularly common, but makes a very beautiful green gem. Tanzania is where we get a lot of minerals that have these green colors. East Africa is a place that has a lot of so-called chrome varieties of minerals because of the sediments that were involved in the metamorphic reactions that gave rise to the gems. Here from Western United States, we have Vesuvianite from Nevada. and it's a beautiful green color. The gem quality portions I've seen have been just millimeters in size. I have not seen a large green gem material of Vesuvianite, but in potential, it's possible you could have a beautiful green Vesuvianite where chromium replaces some of the aluminum. There are other relatively uncommon minerals. Here's spodumene. Normally, we think of spodumene as a beautiful pink mineral due to the manganese found in a lot of the lithium pegmatites. But in North Carolina, in this country, we can get the green variety, Alexandrite variety, or sorry, from Alexander County, we get the variety called hiddenite. And again, we get some chromium replacing the aluminum, and you get these beautiful green colors like we see here. Not very common, but a very beautiful material, not readily available, but a very, very beautiful collector stone. And then we have the chrome tourmalines. These are primarily dravites from East Africa, Tanzania in particular. Beautiful, beautiful stones where you get some chromium replacing the aluminum in the dravite formula. Beautiful, beautiful green chrome dravites. But beware, people of nomenclature. When I have analyzed these chrome dravites, which I have 7, 5 of them had vanadium rather than chromium as the dominant cause of the color. You have both vanadium and chromium occurring in East Africa, in Tanzania and Kenya in particular. So you got to be careful, even though you call it chrome dravite, it could be in fact that vanadium is the main cause of the color in some of these varieties of tourmaline. Now, some less common minerals, collector gems or green minerals for the mineral collector. There are a whole variety of different amphiboles, and actinolite and tremolite are 2 of the most common ones. Those are the calcium, magnesium dominant amphiboles. And it can turn out to be that a small amount of chromium can replace some of the magnesium and iron with maybe a little bit of sodium replacing calcium for charge balance, or other ways to do it. And in this particular case, even though iron is the dominant cause of light absorption, the iron absorbs in the infrared portion of the spectrum where we, the human observer, don't see it happening. Instead, for us, the human observer, the chromium, right here it is the dominant cause. And the chromium in this case is absorbing the reds, letting the green wavelengths come through. So these chromium-containing amphiboles are green-colored, due to the fact, of course, that they have just a few tenths of a weight % chromium that is the dominant chromophore in these particular cases. I've only seen a very small gem variety of these. Maybe some of you have larger ones, but it's not particularly common to get gemstones, but they are beautiful collector minerals with chromium as the color. Well, what about the pyroxenes? Chrome diopside. Again, if we go to East Africa, Tanzania can have diopside where chromium replaces some of the magnesium and then other things going on for charge balance. And other places around the world, in fact, many places around the world can have small amounts of chromium, but in Finland in particular, there can be some really nice dark green chrome diopsides. Another collector mineral, potentially a gem mineral, chrome diopside, where again, chromium +3 in relatively small concentrations, just a few tenths of a weight %, can dominate the color and cause these beautiful colors that we see here. Well, another pyroxene we can't ignore is jade. Jadeite, sodium aluminum silicate. Jadeite, of course, is a very important mineral when it's green in the Asian cultures. I was very fortunate to be able to go to the mines in Asia. Jadeite would be absolutely colorless if it had the ideal chemical formula, sodium aluminum silicate. But it's a small amount of chromium that makes the imperial jade green. It only takes a few tenths of a weight % to make the green jade green. Even though there may be iron in there may be a small amount of manganese in there, it is the chromium that makes the beautiful green color in imperial jade. So let's take a trip to the jade mines in Myanmar and see if we can learn a little bit about the origin of the chromium inside the jade. Here we are in the Hapkant district in northern Myanmar. This is their jade mine number 2. That's the entrance to the mine. It's an underground tunnel system where they are going in, digging away the sediment, and finding boulders of jadeite mixed in with the sediments that they're mining. Here's one of the boulders coming out, being cut open. All of these boulders are cut open so they can inspect them. In this country, we have laws from an organization called California Occupational Safety Administration. I don't think being barefooted and having no safety glasses would be allowed in this country, but nevertheless, they have these big saws cutting open the jade boulders. And when they get them cut open, they lay them out. All of these mines are under military control. And then the head military commander will inspect the mines, inspect the material coming out of the mines, inspect the jade to evaluate them. Here's the head military person at this particular mine with a lamp where he can shine the lamp through a fiber optic probe into the boulder and see the color. Is it colorless? Is it kind of a purple color? Is it basically a green color? And unfortunately, if you look here, you don't see any green. You see very pale material. You see kind of a more of a slightly purpley color here. And in the boulders I saw, which there were thousands of these boulders littering the ground near the entrance to the mine, very, very, very few of them were green. The military inspector, after he inspects it, put markings on these minerals. These markings are an estimate of the quality of the jade, whether it's a translucent jade, an opaque jade, type A, B, or C jade in the market, and an indication of the color quality. And all of these stones will now be sent to down to Mandalay, where they'll enter the jade market, where they'll then be appraised and taxed before they're released to the world. I was not allowed to take any jade, even though there were thousands of pebbles, some just a centimeter in size, some big boulders like this. They would not allow me to take any because they had not been taxed, and they had to be taxed before they could be released to the world's market. Here's a different mine. This is the Golden Dragon Namwa number 109 jade mine. And this particular mine gives us insight into where the green color comes from. This was a massive boulder of jade that was very pale lavender, but where the jade rock was in contact with the metamorphic country rock, you could see the green color kind of oozing in from the country rock. It was the country rock that contained the chromium, the sediments that had built up over time. And then as the various interactions that took place where the jade was being formed at high temperatures deep in the earth, chromium from the country rock was being infused into the neighboring jade along veins, along the edge. And here is where the green color of the imperial jade was found, at the interface between the chromium-containing metamorphic country rock and the large jadeite boulders themselves. Very interesting to see the difference there between them. Well, I have to at least bring in one really, really rare mineral. This is a mineral called painite. It's one of my favorite minerals. This is a mineral also coming from northern Myanmar. And it's a calcium, zirconium, boron, aluminum oxide. At one time, this was the rarest gem known to exist. In fact, if you go to Google and Google the rarest gem, a lot of the sites still claim this is the rarest gem. I was very lucky to go up there, and by pure dumb luck, I was actually able to buy 2/7 of the entire world's supply of this particular mineral. And when we analyzed it, we found that the origin of color in this particular mineral was chromium. We discovered a second locality in the far north for the jade. We told the Burmese scientists the various inclusions that we discovered inside the jade, and within 2 weeks of their knowing this, they actually found the source of the jade, and then hundreds of samples came out, so it's no longer the rarest gem. But again, it's a gem that is dichroic. You get two different colors, whether you're parallel or perpendicular to the C-axis with polarized light. You can attain a very small quantity of beautiful little reddish crystals, and there are only a very small quantity of gems in the world where painite has been faceted into gems. But if we look at the spectrum of this extremely rare mineral, we find again that there can be sometimes twice as much chromium as vanadium. Yes, there's both chromium and vanadium in the mineral, and chromium often behaves very similar to vanadium as a coloring agent. But we see again that the chromium and the vanadium are wiping out the greens, but they're letting the reddish light come through. As you see over here, that's where your Chelsea filter would work. They have a little bit of the bluish light come through, which is more the purpley red color that we see. And then it's pretty well wiping out the further ultraviolet and the purple and the blue portions of the spectrum. So dominantly, the transmission is over here in the green. So I'm very happy to say that we've been able to determine the origin of the color of what used to be the rarest gem in the world, again, where chromium is the dominant cause of the color. And on that happy note, I will say I've come to the end of the discussion of chromium minerals, and I'll be very happy to open it up to you for questions. I need to thank Bill Larson of Pella International and Rob Levinsky of the Arkenstone, who very generously allowed me to use any picture of their products or their website, which featured prominently in this presentation. Okay, people, I turn it back to you.
Extremely well covered. Thank you very much, Dr. Rossman. Just for the sake of interest, I have seen some very interestingly colored, I'm trying to remember now, from asbestos. The brain fails me.
Chrome
Pardon me? No. Pardon?
The chromium containing green grossular from asbestos?
No. The other one. Someone help me here. Quentin or Willow. Hello. Anyway, you did talk about that earlier, and my brain missed it. I'm sorry, but I do think there are some green ones there. Sorry, I've forgotten what it was. That's terrible.
Vesuvianites?
Vesuvianite. Thank you. What's the matter with the brain? Yeah, and I actually have some nice Jimmy crystals of it, so it is possible.
Okay. You've seen something I haven't.
Sorry, I'll take a picture.
Okay. Do that.
Nobody else? Suzanne, have you got a question? Well, I guess that
No,
means
I'm only overwhelmed by the information about chromium, and it was really a great presentation. Thanks a lot.
All right, didn't mean to center you out, Suzanne. So thank you very much, Dr. Rossman. That was very well covered, and I think everybody who attended is now a whole lot smarter about chromium as a chromophore. And for the people who are going to be hopefully joining us again next month and the months afterwards, we have some interesting programs in the offing, and that we're working with the potential speakers. I'm hoping to have one on tourmaline. And I'm hoping, and I've just got confirmation that we will have at least one in our mini series on the finest gem collections in the world, which would be private and public. And I think I can safely say, without releasing too much in the way of information, that we will upcoming have Robin from who's the curator of gems at the British Museum of Natural History, sharing with us some of the amazing stones in her gem collection. It took a while. We had finagle permission from the various people that were able to do that. And so we're going to actually have a tour of the best and the most interesting gems in that collection. So please make sure you keep your ears and eyes open for that when I announce it in the invitations. And I'm not going to say who's doing the tourmaline, but if I finally get a confirmation from them, you immediately will know, because it's a name well known in the industry. So looking forward to all those things. I do hope you'll join us again, and tell your friends to join us, because we're going to continue hopefully throughout the year with interesting, exciting, leading edge gemological programs. So thank you very much, Clemens, for your technological support. It is invaluable, and we really appreciate the time that you give us, and the scientific and technological support you give us that helps this happen every month at this point. Thank you all for joining us. I hope you learned something valuable. And if you have any ideas about programs you would like to see, please feel free to contact me. This program today was a result of one of our viewers suggesting to us that we should have a program on Chromium. So there you go. You can mold the future of our learning, and thank you very much for what you've done to do that today, George. I really appreciate you giving us your time and expertise. And I hope you all appreciate that, how important that is, because this guy's pretty busy. Thank you so much, everybody, for joining us. And thank you in advance for coming next month to see the program, which I think when you see it, you'll be excited about. Okay, so take care. We'll let you know what the program is within the next few weeks. And I hope that you will be joining us and bringing some of your friends along with you. Take care. Have a great day and have a nice holiday when it comes up.
Thank you, George. Thank you, everyone.
Okay, goodbye, everybody.
Mhm.